Excellent. So now we are starting to look at exponential functions and how these actually function. And there's lots and lots of variables. We've got tons of things that, and it looks really, really complicated. The biggest thing that I really want you to pay attention to is notice that k and t are a lot smaller and they're raised up. That means it's to the power of that. And that kt only applies to the b. It does not apply to the A. So let's break each of these things down so that you have a resource for all of these. We've taken notes on this in class, but this is just to help you remember if you have forgotten. So when we look at this, I'm going to start with some of the most useful things. It might not go in order, but I'm going to list them here down below. So when I'm looking at this, I think about the variable, or it's called a constant. The constant a has a meaning of it's the starting point. So if I'm looking at a word problem, this is kind of like where we begin our measurement tool. So if we start, on a certain date and we're counting after that, A is going to be the population or the amount of money or something that happens on the starting point. B in this is our growth rate. Growth, and I'm going to call it a growth or decay, because if something goes down, it would be decay. So if you're losing money, or the population of something goes down, or the amount of land that you have decreases, or the height of a bouncy ball goes down, that's going to be decay, whereas growth is something growing, and that's something that you're familiar with. So growth or decay rate. It's the growth or decay rate. We're going to talk about T. T generally, and some people call this variable n, and this is actually the variable. This is the thing that is changing over time. So this is, I'm going to say this is the variable. So kind of like the x of the equation, this is the variable. And t typically represents the time or the units that pass since the start. So when we did the drug activity in class, the T represented every 4 years. That was really important, that every 4 hours. The T represented a unit of time that wasn't just 1 hour, it was a unit of 4 hours. And this is where K comes in. K is kind of this tricky thing. Most of the time, K is 1, and so I'll write that. Most of the time, for algebra 2 at least, most of the time K is 1. And so we don't really deal with it. As you move on to pre-calculus or something a little bit higher, the K will become different values. But this is the frequency of the event. And frequency is kind of a challenging concept to understand. But here are a few examples. If the population doubles every year, every year, K will be every year, so every 1 year. If it's every half year, it doubles every half year, K is 1/2. If it doubles every 2 years, K equals 2. So you can start to see that K has an impact about how frequently something occurs. Is that when our growth rate changes, how often does that happen? Does it happen every month? Does it happen every year? And K will really change that. As you become more familiar with exponential functions, you'll use K in a lot of different ways. So here's another way to look at an exponential function. It's a little bit different, but it's essentially the same thing. P acts as our a. This 1 plus r is similar to our b. The k and t serve almost exactly the same function. So I'm going to start talking about the things that are different in particular. When I look at p, there's a special name in finance for P. It's called the principal. And it's spelled differently than you talk about, like, this principal of a school. It's spelled differently, Principle. It's principal. And it is essentially your starting point. This formula is used. This formula is used typically when you're talking about growth of finances. So P is the principal. It is the same thing as the starting point. R is the rate of growth. And notice, and I'm going to do this here in red because I want it to be really clear, that if it's growth, the number for R is going to be positive. If it's decay, R is negative. And we're going to do some examples using this exact model because it is a challenging concept to understand. T is time past since start. And K is, again, the frequency. I'm going to invite you to go back to the original page to look up the frequency. But again, for most of our examples, K is going to be 1 because it happens every unit of time, and we'll take care of some of those nuances later. So here's a real-world example of this. We're looking at wolf populations. I'll go ahead and read it out loud. The wolf population of the Pacific Northwest grows starting with 2 mates. Well, mates come in pairs. So there's a male and a female, so for four total. The population doubles every year. So if I go back and I look at some of my equations for growth, I really want to, I'm going to start with my y equals a times b to the kt as my initial sort of template. Well, it doubles every year. And it doubles. The word doubles rings a bell. So my a is my starting point, so I'm going to essentially plug values in. A is my starting point. How many do I start with? I start with 4. B is my growth rate. My growth rate is doubling. Maybe I'll do this a slightly different way. I will start with my A is 4, so I'm going to do 4 in red. And doubling is in blue. So I think about doubling every year. So every year is that K thing, and so my K is going to be 1, and then T is my essentially my variable times T. So if I rewrite this to make it look prettier, y equals 4 times 2 to the power of T. So my starting point, my growth rate, and my frequency every year. So you can see how we can go from an application problem to an equation quite easily, just looking at the equation and analyzing what is what. Let's do a couple more because I think these are quite valuable. So credit card interest on a loan for Christine is 3.46% every month. This month, she can't make her payment and currently owes $277. So if I think about, some of these examples, I'm going to look for a growth rate. I'm going to look for a starting point. So I see a growth rate right here. It's 3.46%. And it looks like I'm going to want to use that finance growth rate, 1 plus r to the power of kt. I'm going to start skipping out on the k because the k is typically 1, so the power of t. I'm looking for my principal, my starting point is that 277, and my growth rate is 3.46%. So 3.46% in number terms, if I want to change that to a percentage, that percentage into a number, it's 0.0346. And so this is the value that we have for our R. I'm going to plug the principal in for the principal. So y equals 277 parentheses 1 plus 0.0346 to the power of t. I'm going to simplify this because I know that 1 plus 0.0436 can simplify, and it makes it easier for us to put into a calculator. So simplify y equals 277 times 1.0346, and we want all of those decimal points. The only reason we would round is if we were getting an answer, but when we're setting up the problem, that 46 really makes a huge impact in the long run. There's 2 more example problems that I want to show you, so stick around with me. We'll go a little bit faster, but we've identified the growth rate, we've identified the starting point, and we're going to keep going. Many banks' customers put their money into a savings account which earns 1%. This actually happens, by the way. They earn 1.1% interest on their money each year. This person starts with $116. So again, I'm going to use that equation. Y equals principal times 1 plus rate to the power of t. Because it's every year, my k is 1, so I'm going to ignore that for now. My principal is this 116. My rate is this 1. We're going to focus on this 1. Remember, we have to convert the 1% is equivalent to 0.01, which is our R. So R is 0.01. I'm going to plug these values in. Y equals the principal, so 116 times 1 plus my rate, 0.01 to the power of t. Simplify that. Y equals 116 to the 1.01 power of t. I've essentially looked for my rate, my starting point, and plugged those values in. We always convert our percentage into just a number. No percentages in here. Last one more. Oh, this one seems like a little bit more advanced, but I think that it's totally within our power to try this. So if I have a bouncy ball, the height is a proportion or a percentage of the ball's previous bounce height. If a ball is dropped from 160 centimeters and rebounds to 120 centimeters on the first bounce, how high will the ball be on the second bounce, the 5th bounce, the nth bounce? This is a little bit different. I'm going to make a table to kind of keep my information organized. So I'm going to make ball. I'm going to do bounce number. I'm going to do height. So if the bounce number is 0, because I haven't bounced it, it's 160 centimeters. On the first bounce, it rebounds to 120 centimeters. We're thinking about 2 and so on, 2 or more. And we don't actually have to continue this, but notice if this is an exponential equation, which it tells me it tells me that it's a proportion or a percentage of the ball's previous bounce, I have to figure out what do I have to multiply here? 160 times what equals 120? And I can use basic Algebra 1 skills. Divide by 160, divide by 160. My bounce rate is 120 divided by 160, which is 0.75. So this is actually my growth rate. And I'm told my starting point, that 160 centimeters. So I'm going to use my special y equals a times b to the t, or the kt. Every bounce, k is 1. My a is my starting point. My a is my starting point, so it's 160. Y equals my starting point, 160, times my rate, which is 0.75 to the power of t. And we should expect that as the ball bounces more, it gets smaller. So if I want to know the second bounce, I put the number 2 in for t. If I want to know the second bounce, I put 2 in for t. So let's do that out. If I want to know the second bounce, I'm going to kind of separate my work here. Second bounce, y equals 160 times 0.75, and it's the second bounce, so I plug in 2. I put this into a calculator. Remember to use the power button. 160 times 0.75 to the power of 2. I get 90. So 90. Now, I don't have to continue this. If I want to know the fifth bounce, I plug in 5. Y equals 160 times 0.75 to the fifth power. 160, parentheses, 0.75 to the power of 5. I get 37.96. So fifth bounce, 37.96. Now when they ask to the nth bounce, I think that's definitely something that's a little bit confusing. When they talk about the nth bounce, they're really saying, after n bounces, how high will it be? And like we plugged in 5 or we plugged in 2, we're going to plug in n. And in this case, we cannot simplify. So the nth bounce, y equals 160 times 0.75 to the n. And that's our nth bounce. I hope this was valuable. I know this was a very long video, but I think afterwards you will have understood how to create an equation out of many different situations. I'll make one more video with a few more advanced types of problems. This last one was definitely challenging.